terceira apresentação, que é um colóquio extraordinário aqui do IFGW, será dado pelo professor Andrew Szentgyorgyi. O Andrew, ele é astrônomo do Departamento de Astronomia da Universidade de Harvard, participa do Smithsonian Astrophysics Observatory, do Centro para Astrophysics lá da Universidade de Harvard. Trabalhou em áreas diferentes dentro da astronomia. Nos vários últimos anos, ele tem trabalhado muito com a parte de espectroscopia estelar de alta resolução, e ele é o pesquisador principal de uma classe de espectrógrafos, né? No caso, é o espectrógrafo G-CLEF, que aparece aqui no título. Ele vai falar sobre isso, então. Ele é o pesquisador principal, e esse espectrógrafo ele será o primeiro instrumento que será colocado no Telescópio Gigante de Magalhães, o GMT. Então, o Andrew vai falar sobre isso, atualmente. So, Andrew, yeah, it was in Portuguese, but welcome and thank you so much.
Thanks so much for having me. It's always a pleasure to be back in Brazil. Sometime in 2014, Tavi invited me to work with her on the Giant Magellan Telescope, and it's great to have an excuse to come back again and again and again. My thesis advisor was an Italian who actually grew up in Brazil, went to USP, England for his PhD, came back and worked in the Constant Grade Laboratory in Rio. So I heard all these stories when I was in graduate school, and it's really just great to be here and visit. So the other thing that's really gratifying is that such a large group of people that are interested in solving one of the more stubborn technical problems that makes it difficult to do the science I think we're going to do that will be very important science. So I always like to start with this picture because if Finiti flew to Earth, and he's flying over the Earth trying to decide whether to land. Is there anything interesting down there? Is there any place to eat? He'd look at this and he'd see that there was life on Earth, and he'd probably come down and find McDonald's and leave again. But anyway, and it's not because of the city lights, because he didn't know those are city lights. That could be volcanic activity or something. What he would see is this green glow. There's a little bit of a red glow. And the green glow is there because solar radiation is stimulating the oxygen in the Earth's atmosphere and causing an aurora. Oxygen is there because there is life on Earth. And the minute life disappears from Earth, specifically plant life, the oxygen will drop to something like a fraction of a percent in a very short period of time. Not good for us because we don't make oxygen. So he sees that and he says, let's go down, let's get dinner. So the plan of this talk is as follows. I want to talk a little bit about diatomic oxygen as a biomarker. Notice not atomic oxygen, diatomic oxygen. Mars has atomic oxygen, photodissociation of CO2 in its atmosphere. Not very much, but a little bit. Diatomic oxygen or ozone, diatomic oxygen. The question is then, why search now? Why didn't we do this? Going faster than I. Why didn't we do this before? Why shouldn't we wait? And argue that this is the moment. This is our chance. Let's talk a little bit about how we find these biomarkers. A little bit about the strategy we're going to adopt with the Giant Magellan Telescope. And a pathfinder search that we like to do in sort of the nearest term possible to look at the star nearest to the sun that has an exoplanet, nearest star to the sun, which also happens to have an exoplanet in its atmosphere. And sorry, this is part of an old talk. I will not talk about the HST habitable world observatory context. As I said before, this is some cyanobacteria. Cyanobacteria is illuminated by the sun with the chemical resources available to it, uses the solar energy to produce oxygen gas, diatomic oxygen. And as I said before, without cyanobacteria, we wouldn't have things like that. We wouldn't have life on Earth as we know it. So a little bit of history. This is the history of the Earth, stretching back to I'm not sure it's something. Stretching from the beginning of the Earth, we believe 4.5 giga years ago, to the present, 0 years ago. And what I've plotted here is the log of the mixing ratio of different major constituents of the Earth atmosphere. So in the very beginning, it was very, very hot. There's no evidence of what was going on. But sometime about 4 billion years ago, continents started to form. We believe continents, the three things that we believe are critical for life to form is first of all, liquid surface water. Liquid surface water, continents, and of course the evidence of all that is that it's formed life as a diatomic oxygen. We believe continents are necessary because in a pure water world, all of the chemicals that would form interesting molecules are so diffuse they can't find each other to make simple organic molecules that then chain together into amino acids, DNA, and all the other good stuff that's necessary for life. So we need continents. But shortly after the continents, we have stromatolites arising. They're the first life forms we know about. They're sort of like enormous gobs of moss. No, not moss, I'm sorry. Primitive cyanobacteria, pond scum, basically. And at that time, the Earth's atmosphere is like Mars, well, probably mostly CO2, reasonable amount of methane, but no evidence for any sort of oxygen or nitrous oxide. Time goes on, and there are these sinks for oxygen. The stromatolites are making oxygen, but silicon wants to make sand out of oxygen, iron wants to make rust out of oxygen. There are all kinds of things that want to form oxides, and there's sinks of oxygen. They're getting sucked up. But somewhere around 2.5 gigayears ago, the sinks are filled and life can start to really do its business and evolve. And you see evidence of this in the ozone abundance and the O2 abundance, nitrous oxide abundance. And life proceeds, and as this goes on, there is an epoch where there's a fairly abundant amount of methane. Now, methane actually goes down, CO2 goes down, and oxygen finally gets to its present non-equilibrium composition of the Earth's atmosphere around 2020. Now, I had this really great idea to search for oxygen. I don't know how many astronomers there are in the room. If you're a ground-based spectroscopist and you take a spectrum, the first thing you see, skip the slide. You take a spectrum like this, there are all kinds of stellar features, but you've got this monster line in 5577, and you just have to throw that data away. You can't observe in that region. It's so bright, it saturates and wipes out your CCD, and I thought, well, here's a chance to actually use it scientifically instead of throwing it away. And so I figured a calculation. It's very hard to do these calculations because agronomists and meteorologists use the most bizarre units. But I finally wrangled them to the ground, and I determined that you would collect 3 sigma signal for the nearest source of stars in something like, 1,000 years. I didn't believe my calculation very much. Fortunately, a group led by Luger et al., led by Luger, actually did it right. And what you see on the left is part of the issue here is what the contrast of your observation is that you can make. And that is your ability to null out the light from the star and only look at the light of the planet. And the conventional wisdom is that to do an Earth orbiting the sun in the optical band, it depends on the band, you need a contrast of 10 to the minus 10. But you can't do that. The best telescopes in the world with the best adaptive optic systems are working about 10 to the minus 4, 10 to the minus 5 on a good day when everything's going well. But nonetheless, they calculated as a function of also resolving power, how long it would take as a function of auroral power in that line. It's sort of an interesting chart. It gives you an idea of what sort of time it takes. You know, if it's 10 terawatts and you've got really great resolving power, then you're probably going to be able to do it in a fairly short period of time, fraction of an hour. But if you look over here, this is where they've assumed that the luminosity is 1/10 of a terawatt. I don't know how reasonable that is, but it was originally, seemed like, okay, ansatz, and then they plot the integration time required as a function of resolving power for different contrasts. And if you get a contrast of 10 to the minus 7, it starts to become an interesting project. But the truth of the matter is we're probably somewhat above the red line. So you're literally talking about thousands of hours for a very high-risk program. On an extremely large telescope, where the time on the telescope probably costs something like $200,000 an hour. Very hard to convince a time allocation committee to give you that. So it was a great idea. It is true, though, that my colleague Avi Loeb, he doesn't just think outside the box, he lives outside the box. Says the way to determine if there's intelligent life somewhere other than the Earth is to look for pollution, because intelligent life forms will undoubtedly develop technology, belch out pollution, and actually, if you look at the different emission features in the Earth's atmosphere, an awful lot of these things are, in fact, pollution, and maybe who knows. Anyway, so a quick study of the crude spectrum of the Earth, and at the very blue end, all of those homopolar dipoles, N2 and O2, produce Rayleigh scattering, so the spectrum arcs up towards the blue. There's some bands for ozone. But they're going to be really wide, so they're not hard to pull out. There's, of course, a slope for vegetation at continental surface because there's a lot of green and brown in the Earth's atmosphere. And then there's water vapor. Water is not a particularly good biomarker because there's water everywhere in the universe. But here at 7,600 angstroms, a fortuitous place to work, very easy to build instruments for, you've got the O2A band. And that's a monster feature. Here it's all been aggregated together. It's a very exquisite bandhead I'll show you in a second. And so we believe that that's the place. You could ask me, are there other molecules? And so this is not my distillation. This is a shopping list by David Catling, who's in Washington, and thinks deeply about what should we look for. So I can't completely justify this as my own intellectual work. But, as I say, O2 is extremely amenable to detection. You could look for ozone in the infrared. The infrared is very much harder, noisier. Another important thing is there are no identified abiotic production pathways. Now, when I gave this talk 3 days ago, somebody said, what about dark oxygen? When they go and they mine manganese nodules, one guy thinks he's seen oxygen. But Science Magazine, Nature, the United States says it's not a good result. So I'm not particularly worried about that. Methane's very interesting. It would be, if we found O2, we definitely have to look for methane, because we would expect it to be there too. But unfortunately, it's not a particularly biological specific gas. And in fact, in giant planets can reach 2%. The Earth's atmosphere, I think, is 300 parts per million. So it's not it's going to be important, but it's not the smoking gun. Ammonia is another interesting biomarker, but it's lots of ammonia in Jupiter. So we don't think there's life in Jupiter. And as you go down the list, it gets hard. Abundances are low, and they're probably undetectable. So oxygen really, I think, is the right place to start. So the next question is why search now? Well, how long was it? 1995, 51 Take B was discovered, first exoplanet ever seen. But it was a surprising exoplanet, right? I mean, all we had were the planets in the solar system, the big planets way outside the ice zone, the rocky planets inside the ice zone. Type 51b was a Jupiter-sized planet with an orbit of a couple of days, way interior to Mercury's orbit. How could that possibly be? And today, this is a really cute plot. The plots is planet radius versus a proxy for the distance from the Earth, the stellar flux you're illuminated with, and then the melting points of different interesting things. And then so this green band in here is in fact what we call the habitable zone. It's the distance from the host star where the planet is not so close like Venus, water to steam, and not so far away where, like Mars, where all the surface water anyway is ice. Habitable zone. And so we see that actually this habitable zone is well populated by all kinds of planets of all sizes and characteristics. So this is a fairly recent development. And, but it certainly is a trigger for this sort of search. This is a chart I made, I think a year ago, so it's probably completely wrong. The story's only gotten better. At that time, all the exoplanets we knew amounted to about 5,500, 600. There were a whole bunch of planets discovered by a satellite called Kepler that stared at 100 square degrees field of view. The trouble is that, and produced many, many exoplanets. Those are faint exoplanets. We need bright exoplanets because to detect a very subtle effect, the presence of oxygen in the atmosphere, you need incredible signals. I'll show you an example where somebody detected CO, but it had to be a monster system. Fortunately, a team at MIT built a satellite called TESS, the Transiting Exoplanet Search Satellite. It now has something almost it has more than 7,000 candidates in its archives. At the time I wrote this slide, the confirmed exoplanets was about 400. I think it's over 600 now. The important thing about TESS is TESS, Kepler satellite had a mirror that was sort of meter class. TESS is a bunch of custom lenses. They're effectively photographic lenses. They're about, I think, 5 inches in diameter. So TESS surveyed the entire sky. And because it had 4 cameras on it, it was able to cover the whole sky, half the sky, in 12 observations, and then flip to do the other hemisphere. The things they find are incredibly bright. And so by the time we get around to searching, I mean, this is plenty to search already. I mean, that's a lifetime's work to go through that catalog, but there will be even more a couple of years from now. And so we now actually have really good candidates to search for biomarkers. So we need to do the search. The enabling things that we need are catalog of bright stars, I just told you about. Most of the stars, in fact, are orbited by exoplanets. That's a surprising result. Most stars have things orbiting. Many of those stars are in the habitable zone, Earth size. Now the problem you're going to help me with, Flavio, is that today there is no true Earth analog. TESS and Kepler measured the radius of the planet, but the mass requires better calibration and better technique overall. And so I'm here hopefully to develop a laser frequency cone will give us the calibration necessary to measure the mass of the true Earth in the habitable zone. Of course, but you measure the mass of the planet by measuring reflex motion of the host star. The host star maximum motion for an Earth orbiting a star like the Sun is 10 centimeters a second. That's how fast the Galapagos tortoise goes when it's walking. Very, very small perturbation, but now we're sort of somewhere at the level of maybe 30 centimeters a second. So with better technology, and a bigger telescope, I think we can do better. Now, one thing is that most stars in the solar neighborhood are tiny stars, much smaller than the Sun. They're M stars, they're red. It's an interesting place to search, but because their M stars are so active, they have so many flares, planet is so close to the star because its mass is lower, people worry that the stellar radiation will sterilize the planet, and it's a very real concern. Search for exobiotic activity consists of first developing a large catalog, done that. Identify a fair sample of Earth analogs by radial velocity method. You and I are going to do that. You too. And then finally, search for atmospheric signatures of biotically produced molecules. Simple. So, just to emphasize how fast this field has moved. 26 years ago, a Canadian graduate student, Dave Sharman, came into my office. At that time, I was the expert on massive photometry at CFA. Came in my office and said, I want to go search for exoplanets transiting their host stars. We measured them by the radial velocity method. First measured the masses, but not the diameters. And so he wanted to see the planet go in front of the star. And I, kid, that's going to be really hard. Why don't you do something like high-scale cosmology? It's easy. But Dave went off and built a telescope on the left, very modest telescope, and he and Tim Brown, in fact, did exactly that science. And in in 2000, they and another group announced the transiting exoplanet. Very important thing, because the trouble is that when you don't know the geometry of the orbit, the mass you calculate for the planet based on the reflex motion of the star is one mass if it's edge on, where the maximum Einstein velocity is maximum, but if it's inclined somehow, the mass of the exoplanet is in fact different. And so with the transiting exoplanetary system, you're looking, it's edge on, and you actually calculate the exact mass of the star. That was a huge thing. Let's see. And this is the original data that they collected. And as I said, it lists the m's, you meant in the pure radial velocity method, measure m psi naught, not m. This is the degeneracy. And for a massive photometrist at the time, it was a vindication of the method. And it also, this now gives you candidates that allows you to probe exoplanet atmospheres by comparing in and out of transit spectra. Now, again, Dave came to my office a couple years later and said he wanted to look for atmospheres. I said, you got lucky that first time, this is never going to work. And so he used SPIS on the Hubble Space Telescope, and he had a filter that was in the sodium D line, and the filter was out of the sodium D line, and compared the depth of the transit off-band and in-band on sodium D. In the sodium D, this exoplanet that he discovered transiting, in fact, it's bigger in sodium D. It's bigger in sodium D because the sodium in the atmosphere makes a bigger effective radius. So, once again, Dave was right and I was wrong. It's not the last time that's happened. So Dave's student, Heather Knudsen, then did a rather amazing thing using, this was IRAC from Spitzer, looked at these are exoplanets, they're the easiest exoplanets. They're giant Jupiters orbiting their star, very close orbits. But so she looked at HD 189-733b and looked at made a thermal map. And so this is a thermal map where the substellar point is at the equator in the central longitude. And the whiter it is, the hotter it is. And as you see here, the substellar point, which you would expect, is, inclination is best for heating the gas. That's not where it's hot. It's hot, it's displaced somewhat. And so this is the first weather map of an exoplanet. And it's evidence for meridional circulation, wind on this exoplanet, moving the hottest point off the substellar. It just gets better as time goes on. Mark Swain used NICMOS on the Hubble Space Telescope to do sort of crude spectroscopy, but nonetheless was able to identify, and again, this is one of the poster child planet sites, a big, easy planet, but nonetheless, an amazing result, see CO2, carbon monoxide, and water. So now, a resolution of about 40. So now we're actually measuring the constituents of the atmosphere. This is all happening incredibly fast. The first exoplanet, transiting exoplanet, was 2009 years later, measuring the constituents. This is a cute result that I include, not because it's so fundamental, but this is an exoplanet spectrum. I forget what this is taken by Dan at Dragomir. Nonetheless, you look at it in this blue end somewhere around 5,000 angstroms. The absorption starts to arc up because of scattering in the atmosphere. So it's there is in fact really scattering going on in this planet's atmosphere. Is it N2 and O2? I couldn't really tell you that, but it answers the questions whether aliens live under blue skies. And now JWST is also doing rather remarkable stuff. This is a fairly tiny star. It's an M dwarf, 7.5 M dwarf, and but nonetheless, in the JWST spectrum, you see waters, CO, you see methane, good thing, but you also see silicons. I mean, this is just great stuff. It's not a very bright star either. So how do you find black mark? Well, as I said, you need a good catalog of transiting exoplanets. Kepler candidates were too faint, but TESS does it for us. There'll be more than we have time to observe with an extremely large telescope. We do need to measure the mass of that exoplanet with precision radial velocity, line of sight velocity measurements, because we do want to actually find a true Earth twin. As I said, M dwarfs we will search, but we believe that an F, G, or K star is the most likely host for a habitable exoplanet. As I said, 10 centimeter second precision, real tough. At the time I wrote this slide, I do recycle my own materials. Spoiler alert. Now I think we're probably more like factor 3 improvement in technique. But what we really need are better instruments and bigger telescopes. Low mass stars will obviously be. So, if you take that divot I showed you in the Earth's atmosphere dummy slide and blow it out, there's this beautiful bandhead structure on 7,600 angstroms. These are all, these tines, which are semi-periodic, are what constitute the A band of oxygen, diatomic oxygen. And so to see this structure, you need a resolution of about 100,000, resolution in the sense of wavelength divided by the resolution element, which we do. That's routine for us to do in the precision radial velocity business. And it's actually been done already. And yeah, again, here you see this, the same telephone number. This is an easy one to do, but nonetheless a very neat result. 14 years ago, Ignaz Stellan is always full of great ideas. What you see on the top is a saucer toward a layer cake of spectrum. So each thing going across is a single spectrum, and they're all stacked up, going T0 to the end of the, well, somewhat past the end of the transit. And so this slice right here is the middle of the transit. And if you look carefully, you see sort of diagonal divot, and that is the CO, bandhead of CO. Now, like O2, it has a bandhead, it has a lot of different features. Ignaz is going to take them all and scrooge them all together mathematically to enhance the signal. But nonetheless, if he does the modeling, the model and the science, it looks right. It's tilted because actually the velocity is changing. And it turns out that you're seeing it blue shifted by about 2 kilometers a second. This actually allows you to do the radial velocity directly of the planet, which is kind of a neat result because it means that you can measure the velocity irrespective about whether it's transit. Nice stuff. Unfortunately, the transit method is going to be very hard. This is a picture taken from probably the space station, and it shows the Earth's atmosphere with the sun in the background. And the thing is that the whole cross-section of the atmosphere is 1% of the Earth's radius. It's a very skinny torus, and so it's not a big signal. So it's going to be pretty challenging. What would be much better is if we had a target that was the whole surface, the size of the whole surface of the exoplanet, but that would require what we call reflection day-side spectroscopy. But that would make things much easier. My colleagues, Mercedes Lopez Morales and Florian Rodler did a very detailed study. This is one chart from it, where they asked for a volume 20 parsecs radius. How long will it take? Assuming you have an Earth-like exoplanet orbiting a star like the Sun, how long is it going to take? Well, not like the Sun, orbiting a star. How long is it going to take to accumulate enough data with the transit method to actually get a phi signal? And she does it by stellar type. G2 is what the Sun is. M9 are the tiniest red dwarfs. And you need a substantial number of transits. And they put everything in here. They have put in the fact that you only get to observe at night, the statistics, you only get to observe at night, 20% of the time it's rainy, or the telescope, everything. They put it all in there. And the answer is that if you're just sort of have average luck, a system like the Earth and the Sun takes 37 years. Now, if your thesis advisor tries to get you to sign up to this, find another thesis advisor. The numbers start to look more realistic towards the low mass end of the M stars, but they are sort of decadal scale things. And astronomy, we do decadal scale things. And some of our surveys go on for 10 years to accumulate enough data. Time allocation committees never give us enough time. So that's not crazy, but it's still a long time. So we have been, many people, my group, have also been working real hard to be able to do what we call day-side spectroscopy. And that's where the light comes to the star, bounces off the surface of the planet, and then you see the reflected light. The first thing to observe, first advantage to observe in this method is that if I'm an alien sitting on a planet orbiting another star, looking at the Earth, and it happens to transit, it's a year. It transits for 13 hours. You get 13 hours of data here. That's why it takes it. On the other hand, with reflection spectroscopy, I think, it will depend, but you might, and be worried, it doesn't have to transit anymore. You might be able to get even more than pi of the orbit. So you get a huge advantage. Also, if your 13 hours are coming up in 6 hours and the clouds roll and it rains, that's it. But if it rains here, you'll get it later. There are other advantages to this too, so argue for it, and that is that all the oxygen in the Earth's atmosphere is in the troposphere. So that 1%, which is the top of is the exosphere, or the thermosphere they use. There's no oxygen up there. It's all concentrated in a ring that's about 8 to 12 kilometers thick. And there's no guarantee that the ray that you're looking at, you point your telescope and you're catching one of these rays, they're going to be refracted. You're not sure that that ray actually even went through the troposphere. It limits your signal a lot. With the reflection method, you know that the light has been through the atmosphere. Not been through the atmosphere, but through the atmosphere twice. And so this is really a huge advantage. So if we can get the reflection spectroscopy technique working, We'll get this answer. The problem is that, as I said, if you're totally naive, you need a contrast of 10 to the minus 10. In other words, you need to suppress the starlight by a factor of 10 to the minus 10 by coronagraphy to be able to see the exoplanet for Earth's sun system. And as I said, we're working on the 10 to the minus 4, 10 to the minus 5 level. But I'll explain how I think this is going to be made to work a little bit later on. So anyway, just to review I've said most of this already. Transits are rare. Reflection spectroscopy you can do all the time. The exoplanets need not transit, so all of a sudden your catalog's much bigger. If you have to transit, catalog is relatively small. Now you have thousands of exoplanets you can do. The other thing that's kind of neat is you obtain the orbital elements directly. You don't have to depend on this very tricky measurement of stellar velocity. The planet is moving pretty fast, so you can measure that directly. And but we do need a new technique, and so the Giant Magellan Telescope strategy. Well, as I think you all know, there are 3 groups in the world trying to build extremely large telescopes. The extremely large telescope, which is now being built on Amazonas in Chile, outside Antofagasta, is almost 40 meters. The enemy American team is 30-meter primary, and we're a modest 25.4-meter primary. The TMT is the only one that will be in the hemisphere. Both us and the ELT will be in the southern hemisphere. US versus European consortia. But the question is, what are we building to do exoplanet science on each one of these telescopes? And on the TMT, they're building a spectrograph that works in near infrared. Will not be able to do oxygen A band. It's actually, they're still horsing around thinking about it. I don't think they have really what you call design yet. We are actually, AIT stands Assembly Integration Test in instrumentees. That's in progress. I'll show you some baby pictures in the end. And it's an optical spectrograph, actually presciently designed to optimize for biomarker search. The ELT is way behind. They've had some political problems with getting their instrument off the ground. It wasn't one of the first flight instruments. They're having money problems, and the design is still fairly early phases. This is the telescope we'll put it on, as I said. One thing that I think is to our advantage is the other telescopes all have these small facets. They literally have, nearly thousands of mirrors that have to be co-aligned and stuff. We just have 7 big mirrors. We know how to make these mirrors. Most of them are already made. Our field of view can be really big. Not important for my science. Other science, a wide field of view allows all kinds of stuff that the other telescopes can't do. If you're an astronomer, the fact that it has a good image scale, it's not too big, is a huge advantage. The adaptive optics is in the secondary, so as opposed to being a separate piece of kit down at the focal plane, and so it has very high throughput. So although we're a smaller telescope, we win a lot in terms of we're effectively bigger than we would be if we did adaptive optics the way either the ELT or the TMT do it. So the size comparison isn't terrible. And then most importantly, we will have extreme adaptive optics first light. I'll just let you look at this. These are the characteristics of the extreme adaptive optic system. The only important thing, this has already been a prototype that's already working at the Magellan Telescope. turns out the only important thing really is this little circle. It is also the only adaptive optic system in the world that's been conceived and it now operates that works down to H alpha, 600 nanometers. All of the other systems are near infrared, so you can't do reflection light spectroscopy in the optical on the other adaptive optics. So just fun fact. So, we're building the GMT. We don't have all the money yet. There's a place for the foundation. There are people beavering away. We have dormitories and workshops. It's happening a little more slowly than we wanted. Overall, the U.S. Our dream is to build the U.S. two extremely large telescopes, one in the northern hemisphere, one in the southern hemisphere. We'll start to learn about that in December. The NSF, National Science Foundation, our funding agency, will start to announce what they say they're going to announce what decisions they're going to make. It's a pretty powerful suite because although GMT is pretty far, about 30 degrees south, and TMT is about 21 degrees north, we share about half the sky, a lot of the galactic plane. So, little name will want to bring something. My particular instrument looks like this. I'm not going to trouble you with too many details. We connect it with an optical fiber to minimize mechanical inferences. That blue thing is we cut it in half. Steak knife. That blue thing is a vacuum chamber. We put it in a thermos bottle to keep it thermally stable. One end you see my former assistant scientist, Sagi Ben-Ami, who's now a professor at the Weizmann Institute. On the right, Juliana Garcia Mejia, who was a graduate student who helped on G-CLEF and is now a fellow at MIT. It's a work of many hands, many different institutions, Smithsonian, Harvard, Arizona, Carnegie, Adolfo Ibáñez in Santiago, University of Chicago. I remember these things. GMT, CASI, the Korea Astronomy and Space Sciences Institute, Taiwanese Asia A, of course, USP, Steiner Institute, and the Weizmann. So let me just finish here. Yeah, I have about 50 minutes or something. So the truth of the matter is that it's the National Science Foundation, which they will not do. On Christmas Day, takes out its checkbook, check for $1.6 billion. We will see first light something like 2031, 32. I'll be 78, so somebody else is going to have to install it. But in the meantime, we got permission to take the spectrograph, which I showed you in the picture. There's a whole other kit that interfaces to the telescope, and bring it to, not going to bring it, take to Magellan. And there are two Magellan telescopes, each 6.5 meters, considerably smaller than the GMT, but it's on the same side. It's plus components. So in principle, when the GMT is built, take G-CLEF, throw it on a truck, and drive it over. We'll be a little more careful. But, and so the Magellan Extreme AI system, the one that works down to 600 nanometers, is already there and working. I mean, it's complicated. They're learning how to use it. And we can interface to it. So we can actually start learning how to do reflection light spectroscopy. Now, I am not delusional, and I think the first time, nobody has ever actually taken an optical fiber at a telescope, taken an adaptive optic system, and put starlight into that fiber. So I really expect a few surprises, and it may take a couple of years to get this all right. It's not, we're not just turn it on, okay, take data, we're going to bed. So it's a really great opportunity to test our approaches. A night on Magellan costs $50,000, $250,000 now. But the GM, I don't know what the GMT is going to cost. United, the GMT is probably going to be $2 million. Costs are going to be staggering. And so if you're going to have to experiment and fool around and make operators sit around and fix things or adjust things. You want to do it at a cheaper time. You'll get a chance to do it. And it gets another observational opportunity. The nearest star to the Earth is Proxima Centauri. And it turns out Proxima Centauri is not a star like the Earth. It's an M. So it's dwarf star. With all the caveats I've listed before, but nonetheless, there is a exoplanet measured by the precision radial velocity, not the transit. And that planet is in the habitable zone. And so it makes a kind of neat opportunity. And it allows us to also test the following hypothesis. My colleague, Christoph Lovas, led a team that did a study of taking an existing instrument at the very large telescope that ESO runs at, up north, called Espresso, and coupling it to a AO system called Sphere to try and do the following thing. Do something that we call the high contrast, high resolution technique. So either high contrast or our resolutions are about 10 to the 5. Our contrasts we can achieve are about 10 to the 5. We've got a good system, and the system at Magellan is about as good as it gets. And so Christoph argues fairly cogently that the convolution of those two effective contrasts can get you to 10 to the minus 10. So all of a sudden, you're in an interesting machine. And that would be for the very large telescopes, a little bigger than Magellan, that's 7,500 angstroms. And so even though we're a little bit smaller than the VLT primary, there are actually 4 VLT telescopes, a single VLT primary, we think it's worth the time. So we're going to give that a try. We can't do, this is sort of a bunch of candidate exoplanets. And so this is the angular separation. And the really important data here is the distance in terms of the diffraction limit. So these stars along this line require the diffract perfect AO. And we don't have perfect AO. This is 2 times the diffraction limit. And that's pretty doable. 2 lambda over d. And if you follow this line up, you see that Proxima Centauri is right here at 2 lambda over d. It's a really big candidate. Obviously this is not for the faint of heart. The Europeans are on our back. The original proposal was turned down for some reason because of how Espresso was configured. It was going to cost tens of millions of euro to implement that original concept. So now they're building something called the Ristretto that is designed exactly to do the science. They will be ready in 2029. Our goal is to be at Magellan in 2027. Does it really matter who gets there first? I don't think so. If somebody gets a positive result, you're going to need a second team to also get a positive result. So even if we were late, it'd be okay, but we're not going to be late. Let's see. All this stuff before, so let me keep going. One quick experiment. One experiment that we really want to do is Mercedes Lopez Morales wrote a paper, full disclosure on that paper. It said that these are the O2 band heads. That we currently, our maximum resolution is currently around 100,000. If we could bump that up to 300,000 or 400,000, the blue is 300,000. You would increase the contrast of this feature somewhere as you approach 500,000. With AO, we can actually do that experiment. We can run it to implementing a mode where you can go to 400 resolution. That's a neat thing. So let me just we're building G-CLEF. This is the Echelle grading. It's a diffraction grading that's the primary dispersion. In fact, that brown thing is a zero couch that we sit in 3 different gratings. Turns out the biggest grating in the world is the size of that silver thing on it, which is a grating. We've now gotten all the gratings and we're aligned. We have to align them very, very exquisitely, sort of submicron. We do that within a parameter. We're working on it right now. Last slide I saw, this looks highly successful. One way we hope to make it better than other instruments is our optical bench. It's a thing that has to be thermally and mechanically stable. It is the first optical bench ever made out of carbon fiber epoxy, which is has the lowest CTE of any material known to man, coefficient of thermal expansion, excuse me, other than 0. That stuff, that brown stuff is 0. It's hard to make. There is a glass. Very hard to make something like that, which is about 4 meters by 2 meters by 2 meters out of glass. So that we think that'll help. We also make, this is a thing that holds one of the mirrors. Mirrors are sort of this big. That'll be highly stabilized. This is testing one of our lenses. This is the first, it's actually 7 lenses altogether. We did finish the testing of the lenses. It's 5 times better than it needs to be, but we're going to use that. This is one of the smaller mirrors. It's about this big. This is my Korean colleagues building the calibration system. This is our testing apparatus for the lenses. This is the 7-element lens. It's a fairly complicated thing because we really simulate the telescope monochromatically. So, stop there.
Obrigado. Thank you, Andrew. We have time for question. Claudia, please. Thank you, turn this on.
Thank you very much for this very nice talk, Andy. I have 2 questions. The first one is the pictures you showed are really amazing. How G-CLEF is so advanced. I had no idea that all these things are already built, like the thermal box that you already have. So are these parts the ones that are going to be taken to Magellan?
This is all for Magellan. I mean, these are all spectrograph parts. The truth of the matter is that the instrument itself consists of 2 pieces. I mean, there are other pieces, but the big pieces of the spectrograph itself, and then the thing that actually connects to the telescope, which is pretty complicated. The telescope, we got so far ahead, they kept changing the design of the telescope. And so we would change our design, say, oh, no, we changed it again. So we finally gave up about 5 years ago. They had finally finalized the design of the telescope. It's actually, somebody's building it in Illinois. With the telescope mount, not the whole telescope. The folks the mirror and the secondaries. Now that that's locked, when we get done with this round of hardware implementation, we're going to go back to the design of what we call the front end telescope.
Thank you. My second question is about the previous slide that you showed with the number of test objects that still need confirmation.
Yeah.
So I would say like more than 5,000 still need confirmation. And for that, for example, you could use small telescopes to do that. But then how would you prioritize that? Would you go first to the K and G stars, or you go to the M stars? Because how should you do it?
Whenever possible, I start with G and K. But as you know, the sky isn't always your friend. Sometimes you're just, there's so many things up that you can't do all of them, and other times, the pole is up and you're kind of, then you're going to do next.
Okay, but you start with G and K.
Yeah.
Thank you.
Everyone, Andrew, when you mentioned that resolving power can go beyond 100,000, is this more an advancement on the grating itself?
Unfortunately, this is a hard lesson to teach. It's a fundamental of optics themselves that if you have an instrument on a telescope, near a certain size. If you double the size of the telescope, you double the size of all the optics. Right now, for the biggest lenses in the world, optical. There's some optical glasses that are bigger, 300 millimeters, 400 millimeters, something. And so we're right at 6 and 8 meter telescopes. You need those biggest lenses in the world, but they're just commercially available. You can't get bigger lenses, so you hit the wall. So to do 100,000 at the GMT, we do is we treat the GMT as 7 8.4 meter telescopes. That's what enables us to get to 1. It's actually 10,000. The thing is that if you, with adaptive optics, your median seeing the image of the star is about 8/10 of an arc. You turn on adaptive optics, you go down to about 8 times smaller. And so the way to increase the resolution is either to increase the size of the beam of the spectrograph or make the slit smaller. So with adaptive optics, we can make the slit smaller. In principle, might be able to get up to 800,000, but your other things start to make life complicated. So our plan is.
When you say that no one has launched adaptive optics corrected beam into an optical fiber, is this really?
People have been. There's the big international telescope meeting perhaps 2 years last June. There are a whole bunch of talks about trying to do it in the infrared. And there's one group that is starting to approach being successful. All the other people that presented for infrared fibers said more data is, when people don't have an answer, more data is needed. Very, very, very tough. The infrared, they're doing it in the infrared. There is no other AO system in the world other than it's not mine. They're the only people that were visionary enough to say we can work that.
I have a general question about how all this data is processed and you decide if you have the atmosphere that you need or not. It's like, do you have like dynamic algorithms, AI, use AI for that, or is it offline processing for everything? All of this is handled.
We'll have to write, there's in astronomy, you sort of have 2 chunks of software. There's one that basically just turns the raw data into analyzable data. Having done that, then have interpretive software. So we're going to have to write what we call the pipeline, get the raw data, take out the bad pixels, flux calibrate it, determine what the wavelength scale is, actually measuring the wavelength scale is a frequency. Very hard to do, actually. Very, very important. We're going to have to write that. We haven't done it yet, to be honest. How we will interpret it is usually up to the observer. So the truth of the matter is just that to do this science, you need a large team. So there will, as we get closer to first light at the GMT, no doubt a team will coalesce. There'll be a Bayesian expert, there'll be a stellar spectra expert, there will be a calibration expert. All these things, you need a lot of, it's not just one guy just can't sit down, get into Python, take things from GitHub, put something together. Take a team. It's more like, unfortunately, more like high energy physics. Astronomy used to be. That team doesn't exist.
So something that exists.
And so I don't know what AI is going to do for us. When people say, well, what are you going to do when you have AI? And I say, I've been using AI for 15 years. Google has been correcting and said, the next letter in your email wants to be this letter. You go, that's AI.
Andrew, So I remember one of the Zoom meetings, you mentioned the potential impact of having a column operating at blue frequencies.
Yeah.
Deep in the blues are part of the spectrum. So how does that fit in with the oxygen detection here?
The column will be useful for oxygen. Don't get me wrong. Accurate wavelength calibration, you always do better with better wavelength. But the comb is critical for the mass measurements. And so what you're doing is you're measuring the radial molecules, the star, not the planet. And there's reason to believe combs work reliably only down to about 5. Aster comb, Menlo system cells, reliably only down to about 5,000 angstroms. You can push them down towards 4,000, but the photonic fibers tend to degrade. It needs to be repaired every 3 weeks or something. And getting a Menlo systems repairman, Las Campanas. So I've heard that they will issue you a service contract, but it costs $100,000. And so the truth of the matter is that my expectation is not that I will have a comb that will work. G-CLEF goes all the way down to 350 nanometers, fairly revolutionary. There are many estimates that say the information content for mass measurements between 5,000 and 3,500 angstroms is 68% of the. So it could be a huge thing. To do that, I think what we're going to do is actually, our primary reference will be etalons. Highly stabilized etalons, got some experts that know how to do that and have done it before for astronomical applications. But the comb is crucial because we're going to then bootstrap the calibration maybe 3 times a night and morning, dawn, and dusk against the laser. So the laser is a key player in all of this. The advantage of using the etalon is that if the laser never breaks, that's great. Right now, you have to confront the reality. You may have your laser break, and you may not get it fixed for, if you're lucky, a week, maybe 3 weeks. If you're using the etalons will continue to function as calibrated because they're going to drift. Not as good as one that's referenced at least twice a day, but you can continue with the etalons. And so you don't have this sort of ugly thing about, well, you're calibrating with a laser frequency comb, it breaks, and now you shove the etalon in and it's a different calibration. Sure, you know that calibrating against the same thing every time is so much better than somebody else saying, oh yeah, well, here, don't use that yardstick, use this. Oh, by the way, it's 2% shorter.
Questions? Andrew, maybe I missed something, but the reflection spectroscopy of the exoplanet atmosphere, is this already done, or is that? No, not yet. Okay. Okay, any more questions?
Thank you, Andrew, for this very interesting talk. I have a curiosity about, are there any interesting features in the deep ultraviolet that can indicate some?
We can see 350 nanometers is kind of the limit for atmospheric transmission. There's some people work out, well, some people work to 3,000. They go really into what you see. You don't get many photons. The atmosphere. Reasonable to work to 3,200. The problem, when you go below 350 nanometers, is that all of a sudden the catalog of glasses that are available to you to make spectrograph camera boil down to fused silica and calcium fluoride, end of story. So to get color correction below, there's a whole catalog of glasses, of eyeline glasses. Eyeline is mercury eye. There are a whole catalog of glasses that stop at about 365 nanometers. You can push to 350. If you use those glasses at 320 nanometers, You're not going to. So you get, all of a sudden, if you only have 2 glasses, you have 14 or 15 lenses. Sort of absurd for what I want.